Another powerful tool in this chapter is the concept of the parallel axis theorem. Okay, so earlier we found the moment inertia about the center of mass, let's say for a thin ring, about an axis that passes through its center of mass in this orientation. Okay, and remember, this is the expression for moment inertia, okay, about an axis for a mass distribution, okay, not a point mass, okay. So remember how we did this, okay. We said r is the distance out to the mass element dm, okay. Well, the mass element dm, okay, is along the ring, and as I integrate along that ring, the radius is constant, so it comes outside, okay. It's just capital R, and I integrate dm and I get mr squared. So we did that in the notes, that the moment inertia about that axis, okay, moment inertia about that axis is just mr squared, okay. And remember all the different forms, we had 1/2 for the disk and 2/5. Here, all the mass is as far away as you can get, so that's why that coefficient is a 1. Okay, now instead of looking at the moment inertia about the axis through the center, what if we had a nail, okay, or where we put the ring, okay, pivot on a nail or pivot on your pencil, okay, like take an empty roll of tape, okay, there's your empty roll of tape, okay, and hang it from your pencil, there's your pencil, okay, and eventually we'll do something like this and make it a pendulum. And we want to ask, what's the moment inertia of the ring about this axis A, all right? Well, if we try to do that, okay, the integral of r squared dm, so r is a distance from the axis of rotation out to the mass element dm, okay, as I integrate the dm, all right, that r is not constant, okay, so that integral is really hard to do. So what we do is we have something called the parallel axis theorem. And I think if you go into files and lecture notes, there's a proof of the parallel axis theorem. It's a big mess, okay, so I'll tell you right now, you don't have to know the proof of the parallel axis theorem, okay, don't worry about that. And I think it's in the book as well. Okay, but what the parallel axis theorem says is, if you know the moment inertia about the center of mass for a body, kind of like this one up here, okay, if you know that moment inertia, then you can easily find the moment inertia about any other parallel axis that's a perpendicular distance h away. Okay, now all that means, okay, is let's say I have, this is a disk, okay, and I know the moment inertia about an axis passing through the center of mass, okay. Now I want to pivot it up at that point, okay. So this is the old axis, okay. So this axis here, okay, that's my old axis, and now I'm a perpendicular, it's kind of hard to draw that, so I'm a perpendicular distance h away, okay. So these two axes are parallel. So hence the name of the parallel axis theorem, okay? So here's a side view of it. So here I have a disk. I know the moment inertia about the center of mass, but instead of rotating it about that axis, I want to rotate it about that axis. So these two axes, okay, the new one that I want to find the moment inertia of, and the old one, whose moment inertia I know, those two axes are parallel. And the distance between them, distance between those two axes is h. So the parallel axis theorem says, and it's really that easy, that if I want to find the moment inertia about that new parallel axis, it's just the moment inertia about the center of mass, the one I know, plus m8 squared. Okay, it's that simple. Okay, the derivation's a big mess, but that's what pops out. Okay, and h is that distance between those two axes. So in the problem we were just trying to do, okay, there's the hoop. Okay, we knew the moment inertia about that axis. Now I want to find the moment inertia about that parallel axis. Okay, well, the parallel axis theorem just says it's I center of mass, that's the one we always know, plus m8 squared. So I center of mass for the hoop is mr squared, and h is the distance between those two parallel axes, which is just the radius. Okay, so right there I put my mr squared, that's the moment inertia, the one I know, and now I get the moment inertia about that axis up at the top. Okay, that axis is 2mr squared. So the parallel axis theorem has the integration in it. Because if you look at the derivation, it's done with integration. Okay, now here I have a disk. okay? And I want to find the moment inertia of this disk about that axis, okay? An axis that's parallel to the the center of mass axis, whose moment inertia I do know. So the moment inertia about that parallel axis theorem says it's I center of mass plus m8 squared. Okay, well, it's a disk, so I know I center of mass, and h is the distance between those two parallel axes, which is r. So the moment inertia of this disk about that axis, okay, is 3/2 mr squared. Okay, and again, the parallel axis theorem has the concept of integration in it. Okay, now hopefully we'll get to the lab in which you'll have a disk, you'll rotate it about, okay, its center of mass, okay, and then you'll rotate it about that axis, which is off almost to the edge, okay, to the edge, and you'll take the disk and rotate it about an axis that's not even on the disk itself, okay. So the disk is way out here, and you're going to rotate it around that axis, okay. So to find the moment inertia about that parallel axis, it's I center of mass plus m8 squared. Okay. Now, some books use capital D, some books use H. Our book uses H. Okay. In the lab, I used a capital D. Okay. It doesn't matter what letter we use. Okay. So it's a distance between those two axes. So I center of mass for the disk. Okay. That's the moment inertia, or that's the axis about whose moment inertia we do know. That's the 1/2 mr squared plus md squared. All right. So we're going to see in lab, okay, that the moment inertia about that parallel axis, okay, goes as some constant times this distance d to the n. Okay. So we'll also see, okay, we'll find that exponent, and we'll see that the exponent is 2. So what that means is that if I have a disk, okay, there's the disk, and I'm rotating it about the axis, and I can find the moment inertia. Okay, if I take the disk and I triple, okay, multiply it by 3, I triple the distance. Okay, so if d increases by a factor of 3, okay, so if I triple that distance, what happens to the moment inertia? Okay, it goes up by a factor of 9 because of the square. Okay, so we'll actually see that in lab, that if you rotate it about some axis here, okay, there's my disk, I rotate about some axis, there's distance d, okay, if I do 1, 2, 3, if I triple that distance d, okay, so d increases by a factor of 3, we'll see in lab that the moment inertia increases by a factor of 9. So the parallel axis theorem is a really powerful tool.